There's a moment in the history of science that doesn't get nearly enough credit. Not a discovery made in a gleaming laboratory, not an announcement from a space agency with cameras rolling. It happened, in a sense, on paper, in the middle of a war, written by a man dying on the front lines, in the trenches of World War I. Karl Schwarzschild was a German physicist serving in the artillery corps in 1915 when he got his hands on something that had just been published by Albert Einstein. A brand new theory, general relativity. And instead of setting it aside, Schwarzschild read it, worked through the mathematics while shells were falling around him, and within weeks sent Einstein a letter containing an exact solution to his equations. Einstein wrote back, genuinely astonished. The solution was clean, elegant, almost too elegant. But it contained something troubling, something that made even Einstein uncomfortable. Hidden inside the mathematics was a point, a single location in space, where the equations didn't just produce a large number. They broke. They produced infinity, division by zero, a place where space-time itself seemed to collapse into a singularity that the laws of physics, as written, could not describe. Einstein's response for years was essentially, this can't be real. It must be a mathematical artifact, a glitch. The universe, he insisted, would not permit such a thing to actually exist. And here is where the story gets genuinely strange, because the universe was not waiting for Einstein's permission. For decades, physicists treated Schwarzschild's result as a curiosity, something the math was technically allowed to produce, the way an equation might technically allow a negative number of apples. Possible on paper, meaningless in reality. The idea that space could curve so severely, that gravity could become so intense that not even light could escape. It seemed like science fiction written in the language of calculus. Then, observations started arriving that didn't fit the comfortable picture. Stars moving in ways that required enormous invisible masses at their centers. Gas spiraling at impossible speeds around regions of total darkness. X-rays blazing from parts of the sky where nothing visible existed. The universe was sending signals, and the signals were pointing back to the thing everyone had agreed to dismiss. What Schwarzschild had found wasn't a glitch. It was a door, and on the other side of it was a class of objects so extreme, so fundamentally disruptive to our intuitions about space and time and matter, that physicists are still arguing about what they actually are. The night the universe stopped making sense wasn't one night. It was slow, it was reluctant. It happened in stages, each one requiring us to give up something we thought we understood. And the first thing we need to give up is the picture most of us carry in our heads, because chances are, what you think a black hole is not quite what a black hole actually is. So let's get something straight right away, because almost everything popular culture has taught you about black holes is either incomplete or outright wrong. Black holes are not holes. That's the first thing. The word hole implies an absence, an emptiness, a gap in something. But a black hole is the opposite of empty. It is a place where matter has been compressed to such an extreme that it has fundamentally rewritten the rules of the space around it. Not a void. A density so savage it bends reality itself into a new shape. Most people picture a black hole as a kind of cosmic drain. A dark circle in space, slowly sucking everything nearby into oblivion, like water spiraling down a bathtub. That image is wrong in almost every detail. Black holes don't suck. They don't reach out and grab things. Gravity doesn't work that way. If you replace the sun with a black hole of identical mass, which would be terrifying for other reasons, Earth would continue orbiting exactly as it does now. Nothing extra pulling, nothing reaching, just gravity, the same gravity, doing the same job. The danger isn't in some predatory hunger. The danger is in getting close. Now here is where the physics gets genuinely strange. A black hole is defined by one fundamental feature, a boundary called the event horizon, not a surface, not a wall. A boundary in space-time, a point of no return, beyond which the escape velocity exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing that crosses that boundary ever comes back. Not matter, not radiation, not information. The event horizon isn't made of anything. You couldn't stand on it, you couldn't touch it, and yet it is the most consequential threshold in the known universe. Inside that boundary sits the singularity. And here is where physicists will be honest with you in a way science documentaries rarely are. We do not know what a singularity actually is. The math, Einstein's own equations, predicts a point of infinite density, a place where volume reaches zero and mass becomes infinite. But infinite density is not a description of physical reality. It is a description of a broken equation. When your math produces infinity, it means the theory has hit its own wall. General relativity, the same framework that predicted black holes in the first place, cannot describe what happens inside them. That's not a gap in our knowledge we're about to fill. That's a fundamental limit. So what we have is this: a region of space enclosed by an invisible boundary, containing something we genuinely cannot model, radiating nothing we can directly detect, and yet shaping the structure of galaxies across the entire observable universe. Black holes are the most real and the most mysterious objects physics has ever encountered. They exist. We have seen their shadows, measured their influence, heard the gravitational waves from their collisions, and we still cannot fully describe what they are. Which raises the obvious question: where do they come from? How does ordinary matter, hydrogen, helium, the same stuff your body is partially made of, end up compressed into something that tears a hole in the logic of space-time? That process is one of the most violent events the universe is capable of producing. And it begins with a star making a decision it cannot survive. A star is, at its core, a negotiation. For millions, sometimes billions, of years, two forces are locked in a standoff so precise it borders on the miraculous. Gravity, relentless and patient, pulls every atom of the star inward. And fusion, the nuclear fire burning at the star's heart, pushes back. Hydrogen crushed into helium, helium into carbon, carbon into heavier elements, each reaction releasing energy, each burst of energy holding the star open against collapse. It's not peace exactly, it's equilibrium under pressure. A controlled crisis that lasts an eternity. Until it doesn't. What breaks the truce is surprisingly simple. The star runs out of fuel. Not all at once. It's more like a fire working through a log, burning the easiest material first, then struggling with what's left. When a massive star exhausts its hydrogen, it moves to helium. When helium runs out, it burns carbon, then neon, oxygen, silicon. Each transition happens faster than the last because heavier elements yield less energy and cost more to ignite. A star might spend 10 million years burning hydrogen, then a few thousand years burning helium, then a single year on carbon. By the time it reaches iron, the end is hours away. Iron is where the negotiation collapses entirely. Fusion only releases energy when it builds atoms up to iron. Past iron, the process starts costing energy instead of releasing it. So when the star's core fills with iron, fusion simply stops. There's no new energy, no new pressure, nothing left to push back. What happens next takes less than a second. Without outward pressure, the core falls. Not slowly, catastrophically. In roughly a quarter of a second, a core the size of Earth compresses down to something roughly the size of a city. Millions of times Earth's mass, packed into a sphere you could cross in minutes. The density becomes almost incomprehensible. Protons and electrons are forced together into neutrons. The entire structure of matter is being renegotiated at a fundamental level. And then the infalling outer layers slam into that suddenly rigid core and bounce. The rebound sends a shockwave outward through the rest of the star. A shockwave so violent it tears the entire outer structure apart. This is a supernova. The star doesn't just die. It detonates, For a brief window, a single dying star can outshine an entire galaxy of hundreds of billions of suns. But here's what matters for what we're tracking. Not every star explodes cleanly and leaves behind a corpse you can study from a safe distance. The most massive stars, those with cores above a certain threshold, the shock wave stalls. The outer layers don't escape, they fall back, and everything, all of it, collapses inward without anything left to stop it. Gravity wins, completely. Finally, the question that immediately follows, and it's a question physicists still lose sleep over, is what actually happens when matter keeps compressing past every known limit, past the density of an atomic nucleus, past anything our equations were designed to handle. The neutron star has a surface, a structure, something you could in theory point to. But push past that threshold and the equations don't just struggle, they break. They return infinities where there should be numbers. They describe something that has no size, no surface, no floor. That's where we're going next. Not just into the black hole, into the place where the physics itself stops making sense. The star is gone. What's left behind doesn't shine, doesn't pulse, doesn't do anything a normal object does. It just pulls. And the pulling doesn't stop. It doesn't reach some equilibrium, doesn't settle into a stable shape. The matter keeps falling inward, past every threshold physics thought it had set, until something extraordinary and deeply unsettling happens. The equations stop working. That's not a metaphor. The mathematics that describes how space, time, and gravity behave. The framework Einstein spent a decade constructing. The same one that predicted GPS timing corrections and gravitational waves and the bending of starlight. That framework produces an answer at the center of a black hole. The answer is infinity. And in physics, infinity is not a solution. It's a confession. It's the math throwing up its hands and saying, I no longer describe reality here. We call it a singularity. And what makes it strange is not just that density becomes infinite, or that volume becomes zero, though both of those are disturbing enough. What makes it strange is that the very fabric those concepts live inside begins to lose meaning. Space as a dimension you can move through. Time as something that flows forward. These aren't just warped near a singularity. They become undefined. The coordinates collapse. The map dissolves before you reach the territory. Think about what gravity actually does to space and time. Far from any mass, space-time is relatively flat, a calm geometry that lets light travel in straight lines and clocks tick at steady rates. Add mass and you curve it. Add enormous mass and you curve it sharply. Einstein showed that gravity isn't a force reaching across empty space, the way Newton imagined. It's the shape of space itself, the curvature that makes objects follow paths they can't resist. The planet orbits the sun not because something is tugging at it, but because the sun has bent the region of space-time the planet moves through, and the planet is simply following the deepest groove available. Now take that logic to its extreme. Take a collapsing stellar core, perhaps 2 or 3 times the mass of the sun, compressed past the density of an atomic nucleus, and still falling, still tightening. The curvature of space-time around it doesn't level off. It steepens and steepens and steepens until space itself is being pulled inward faster than anything, including light, can push back outward. The geometry doesn't just bend, it breaks. Gravity at this scale isn't simply a stronger version of what holds you to the ground. It becomes something qualitatively different. The force you feel standing on Earth is a gentle consequence of curvature. What happens inside a collapsing black hole is curvature without limit, geometry without constraint, gravity that has exited the regime where any of our tested, verified physical laws remain in force. General relativity, ironically, predicts its own failure. It tells you, in its own language, that there is a place where it stops being true. And here's what makes this more than just a technical inconvenience. Quantum mechanics doesn't save you. You might expect that when objects get small enough, quantum effects take over and prevent the complete collapse. Quantum mechanics is extraordinarily good at resisting certainty. Particles don't have precise positions and momenta simultaneously. There's irreducible fuzziness built into the fabric of nature. That fuzziness ordinarily prevents matter from collapsing all the way to a point. But the gravitational forces inside a black hole are so overwhelming that quantum resistance is simply outgunned. The two great theories of modern physics, general relativity governing the very large, quantum mechanics governing the very small, cannot talk to each other inside a singularity. They give contradictory answers, and we don't yet have the language to reconcile them. This is the frontier. This is the actual edge of what physics knows. So what you're left with is a region of space that no known equation can fully describe, created by a process that physics itself predicts with clockwork precision right up until the final moment, and then silence. The machinery of the universe runs perfectly until it runs into itself. But here's the thing. You don't need to reach the singularity to run into the consequences of all this. The breakdown of physics at the center radiates outward in its effects, not in light, not in particles, but in structure. In the boundary, the black hole draws around itself. A surface that marks where the rogue gravity becomes absolute, where escape stops being a question of speed and becomes a question of geometry, where even the concept of looking back becomes impossible. That boundary has a name, and understanding it will change how you think about space, time, and the direction reality is allowed to move. There's a boundary around every black hole that has no physical surface, no wall, no edge you could touch. You wouldn't feel it as you crossed it. No alarm would sound. The temperature wouldn't change. And yet, the moment you pass through it, the entire structure of your future would collapse into a single, unavoidable destination. That boundary is called the event horizon, and it is one of the strangest objects in the known universe, mostly because it isn't really an object at all. Think of it this way. When you throw a ball into the air, gravity pulls it back. Throw it faster, it goes higher before returning. Throw it fast enough, about 11 kilometers per second from Earth's surface, and it escapes entirely. That's escape velocity. Every massive object in the universe has one. The event horizon is simply the surface where escape velocity equals the speed of light. Inside that boundary, you would need to move faster than light to get out. And nothing does that, so nothing leaves. What makes this so disorienting is that light itself is trapped, not slowed down, not bent back reluctantly. Trapped. The photons that enter that region are not fighting against gravity and losing. They are moving at full speed in every direction they're allowed to move, and none of those directions leads outward anymore. Space itself, inside the horizon, is flowing inward faster than light can swim against it. That's not a metaphor. That's the geometry, and this is where it gets deeply strange. From the outside, you never actually see anything cross the event horizon. An astronaut falling toward a black hole would appear, to a distant observer, to slow down asymptotically, redshifting, dimming, freezing at the edge, like an image smeared in time, never quite arriving. You could watch forever and never see the crossing happen. Meanwhile, from the astronaut's perspective, nothing unusual occurs at the moment of crossing. No wall, no jolt, just a threshold that exists only in the mathematics of where they now stand relative to everything else. So who's right? Both. Simultaneity, the idea that events happen at a specific shared moment, doesn't hold in this regime. The crossing is real for the falling astronaut, and it is genuinely invisible to the outside observer. These aren't contradictory stories. They're different slices through a geometry that doesn't behave the way our intuitions demand. And here's the detail that tends to stay with people long after they hear it. If you were falling into a stellar mass black hole, tidal forces would destroy you before you reach the horizon. But for a supermassive black hole, the kind lurking at the center of galaxies, millions or billions of times the mass of the Sun, the horizon is so large that the tidal forces there are relatively gentle. You could cross it intact without knowing, without any sensation of transition. The point of no return, past an ordinary stillness. The event horizon doesn't announce itself. It doesn't glow or roar. It's a feature of the future. a region where your possible futures have been reduced to one. And that idea that space-time can have regions where the structure of what can happen next is fundamentally different quietly sets up something even harder to absorb. Because if the geometry of space changes this dramatically near a black hole, time doesn't come through that geometry unchanged. Time, it turns out, is not the steady universal river we experience it as. And black holes make that undeniable. We left you standing at the edge, that invisible membrane where light itself surrenders. But here's what we didn't tell you yet. Crossing that threshold doesn't just change where you are, it changes when you are. And that distinction is going to unravel something you've carried as a certainty your entire life. Time feels absolute. It feels like a river that everyone rides together, flowing at the same rate for you, for me, for every rock and star in the universe. 1 second here is 1 second there. That's not just intuition. It's the invisible assumption underneath almost every experience you've ever had. Einstein dismantled it. He showed that time is not a backdrop. It's a participant. Gravity doesn't just pull objects. It pulls time itself, stretching it, warping it, making it run at different speeds depending on where you are and how fast you're moving. This isn't metaphor. Atomic clocks placed at different altitudes, one at sea level, one on a mountaintop, drift apart. Not because of mechanical error, because time genuinely moves faster when you're farther from a gravitational source. GPS satellites have to correct for this constantly, or your navigation would drift by miles every day. The physics is doing the work right now, invisibly, around all of us. But that's the gentle version. Near a black hole, the effect becomes catastrophic. Imagine two observers. One stays far away, safe, watching. The other falls toward the event horizon. From the outside, something deeply strange happens. As the falling observer gets closer, the signals they send back, light, radio waves, anything, arrive increasingly stretched and delayed. The observer appears to slow down. Their movements become sluggish, like a film reel losing frames. They redden, they dim, and then, asymptotically, they freeze. They never appear to cross the horizon. They just stall there, suspended, growing fainter until the last photon gives out. Time, as seen from outside, has effectively stopped for them. Now inhabit the falling observer. From their perspective, nothing dramatic at all. They cross the event horizon in a perfectly finite, possibly unremarkable moment. Their watch ticks forward normally. They don't feel themselves freeze. They are not frozen. They have crossed the threshold. They just can no longer tell anyone about it. Two valid experiences, irreconcilable accounts, both physically real. This is what physicists call gravitational time dilation, taken to its extreme, and it forces a question that has no comfortable answer. If two observers experience time so differently that one crosses a boundary the other never sees crossed, what is time actually measuring? Not a universal clock, not a shared stage, something local, something perspectival, something almost shockingly intimate. There's a thought experiment that cuts even deeper. Suppose you could hover just outside the event horizon, not fall in, but hold position, resisting the pull with tremendous force. Every second you spend there, years pass in the universe beyond. Decades, centuries. You'd be a time traveler without moving through time at all, simply by living in gravity's deep well. The mountain and the valley were always running at different speeds. The black hole just makes the difference so extreme it becomes undeniable. What this reveals is that space-time near a black hole isn't just curved, it's undergoing something closer to a phase transition. The radial direction you'd normally use to move outward in space begins to behave like time. In a sense, inside the event horizon, falling inward isn't moving through space toward the singularity. It's moving through time toward it. The future, for anything inside, is not a direction you choose. It's the singularity. Inescapably. The way tomorrow is inescapable for you right now. Sit with that for a moment. Inside a black hole, the singularity is not a place. It is a when. And here is where the architecture of our understanding begins to crack in a very specific way. Because these laws, as clean and beautiful as they are, cannot hold forever. Even black holes, it turns out, are not truly permanent. There is a process, quiet and almost impossibly slow, by which even the darkest thing in the universe leaks away. Not through the horizon, not through anything we've discussed yet, but through something stranger, a mechanism so counterintuitive that even its discoverer reportedly couldn't believe the calculation when it first appeared on the page. We've watched time bend and stretch around black holes, clocks slowing to a crawl, moments frozen at the edge of forever. It seems like nothing escapes, nothing leaves. The black hole just sits there, patient and permanent, swallowing everything that comes close. But Stephen Hawking looked at that picture and saw a flaw. In 1974, he published a result so unexpected that physicists initially thought he'd made a mistake. Black holes, he said, are not immortal. They radiate. They lose energy. And if you wait long enough that the number of years required would embarrass astronomy itself, a black hole will evaporate completely. Gone. Nothing left. The mechanism is stranger than the conclusion. Empty space is not actually empty. At the quantum level, the vacuum is restless, pairs of particles constantly flickering into existence and annihilating each other, borrowing energy from nothing and returning it so fast that reality barely notices. These are called virtual particles, and under normal circumstances, they vanish before they can do anything interesting. But at the edge of a black hole, interesting becomes unavoidable. When a particle pair appears right at the event horizon, something remarkable can happen. One particle falls inward, past the point of no return. The other escapes. And because the energy for that pair had to come from somewhere, it comes from the black hole itself. The escaping particle carries real energy outward. The black hole pays the bill. Do this once, it means nothing. Do this continuously, across billions upon billions of years, and the black hole slowly loses mass. It radiates, it shrinks, it dims like an ember cooling in the dark. Except the smaller it gets, the hotter it burns, the faster it radiates, until the final moments arrive in a violent flash of energy and then silence. The temperature of this radiation, what we now call Hawking radiation, is almost impossibly small for large black holes. A stellar mass black hole radiates at a temperature so far below the cosmic microwave background that it's effectively invisible, drowned out by the warmth the universe itself inherited from the Big Bang. We have never detected Hawking radiation directly. We may never detect it from a natural black hole. It remains for now. A theoretical result of extraordinary mathematical precision and almost no observational confirmation. And yet physicists believe it. Deeply. Because Hawking didn't just pull the answer from intuition. He derived it from the marriage of quantum mechanics and general relativity, the two frameworks that describe reality at its smallest and largest scales, frameworks that otherwise refuse to cooperate. Hawking radiation is one of the few places they agree on something. That agreement carries enormous weight. But here's where the story pivots. If black holes evaporate, if they shrink and disappear, then what happens to everything they ever swallowed? Every star, every planet, every particle of information that crossed the event horizon and seemed lost forever. When the black hole is gone, where did all of that go? Hawking radiation, as he originally calculated it, is thermal. It's random. It carries no memory of what fell in. Which means when the black hole finishes evaporating, the information about everything it consumed has simply vanished. Not transformed. Not hidden. Destroyed. And that is a problem that goes far deeper than one missing star. That is a problem that cuts to the foundations of physics itself. Because quantum mechanics has a rule, one of its most sacred, that says information cannot be destroyed, ever, under any circumstances. So now you have two pillars of modern physics, and they are pointing at each other with contradictory answers. Hawking radiation says the information is gone. Quantum mechanics says that's impossible. Someone is wrong. That collision, that irreconcilable disagreement between two theories we both trust, is what physicists have been fighting about for 50 years. And the fight has been anything but quiet. We just watch something impossible become plausible. A black hole, this object defined by the idea that nothing escapes, slowly losing energy, slowly dimming, eventually vanishing into nothing. Hawking radiation changes everything we thought we knew about black holes being eternal. But in changing that, it opened a wound in physics that has never fully healed. Here is the problem, stated plainly. When a black hole evaporates, where does the information go? That question sounds almost philosophical. It isn't. In physics, information is not a metaphor. It is a technical, precise, load-bearing concept. Every particle in the universe carries information, its position, its spin, its momentum, the exact history of how it got to be where it is. The laws of quantum mechanics say that information is indestructible, not just hard to recover, indestructible. If you burn a book, the information in the text still exists, encoded in the motion of every smoke particle, every photon of heat. Scrambled, yes. Lost, no. Quantum mechanics is built on the guarantee that you could, in principle, reverse any process and reconstruct what came before. Black holes seem to honor this. Matter falls in, information falls in, but the black hole remembers. Encoded somehow in its mass, its charge, its spin. Then Hawking radiation arrived, and the guarantee started looking shaky. Hawking radiation is thermal. That word matters enormously. Thermal radiation is random. It carries no record of what produced it. A burning coal and a burning manuscript release heat at the same temperature, and the heat itself cannot tell you which was which. If a black hole emits purely thermal radiation throughout its entire life and then disappears, the information about everything that ever fell into it is simply gone. Not scrambled, not hidden, gone, annihilated. And that is not just a puzzle. It is a direct, head-on collision between quantum mechanics and general relativity. This became known as the information paradox, and it did not merely confuse physicists, it divided them. On one side stood Stephen Hawking, at least for a long time. He argued that black holes genuinely destroy information. General relativity permits it, he said. The universe, at the quantum level, might not be as reversible as we thought. Information loss is real. Accept it and rebuild the theory. On the other side stood most of the quantum mechanics community, and eventually a formidable champion, John Preskill, among others, who insisted that information destruction is catastrophically unacceptable. Quantum mechanics is not a theory you can patch. It is a framework that the entire structure of modern physics rests on. If information can be destroyed, probability itself stops adding up to 1. Cause and effect become untethered. The mathematical machinery that underlies chemistry, biology, technology, all of it, depends on unitarity, on the rule that information is conserved. You do not casually discard that rule because one equation in general relativity seems to suggest it. The two sides made a bet, literally. In 1997, Hawking and Kip Thorne bet John Preskill that information was lost. The prize was a baseball encyclopedia, a book of information chosen deliberately. For years, the debate was a standoff. Then something unexpected happened, from an unexpected direction. String theory and a framework called the AD-S/CFT correspondence, a deeply abstract construction linking a theory of gravity in certain spaces to a quantum theory on the boundary of those spaces, began to suggest that black holes, when properly described at a deep level, do preserve information, that the radiation coming out is not truly random, that it is, in an almost impossibly scrambled way, carrying the imprint of everything that fell in. The scrambling is so extreme that practically reconstructing the original information would require a computation vaster than the age of the universe to perform. But in principle, it is there. In 2004, Hawking conceded. He stood up at a conference in Dublin, announced that he had been wrong, and awarded Preskill the encyclopedia. Thorne did not concede. He still isn't sure. The scientific community is still not fully sure. Because the concession answered the scoreboard question, information is probably preserved, without answering the mechanism question. How? How does information get out? Where does it hide while the black hole is alive? How does it imprint itself on radiation that originates at the event horizon while the information itself is somewhere deep inside? That question has spawned some of the most radical ideas in modern physics. Firewalls. The possibility that the event horizon is not a peaceful boundary, but a wall of lethal high-energy radiation, which would tear apart any infalling observer instantly. Fuzzballs. The string theory proposal that there is no interior at all, that the black hole is a tangled quantum structure all the way through. Holography. The stunning idea that everything inside a volume of space is somehow encoded on its surface, like a three-dimensional image stored in a two-dimensional film. Each of these ideas is not a small adjustment. Each one proposes that something we thought was solid, the interior of a black hole, the smoothness of space-time, the very geometry of volume, is either wrong or incomplete. And here is what makes this more than a dispute among specialists. The information paradox is not really about black holes. Bizarre. It is about whether quantum mechanics and gravity can coexist, whether the universe is, at its deepest level, consistent. Two of the most successful theories in the history of science point in opposite directions, and black holes are the place where they are forced to fight. We haven't resolved that fight yet. But in trying, we've discovered something even stranger, that the physics of black holes may be telling us something about the nature of reality itself, about what space is, about what time is, about whether the universe we experience is the deepest level of what exists, or just the surface of something far more fundamental. That is where we are going next. We have spent this entire journey treating black holes as exotic exceptions, distant catastrophes written into the fabric of space-time, irrelevant to the ground beneath our feet. But something shifted in the last few decades of physics. Quietly, almost reluctantly, the equations started whispering something uncomfortable. Black holes might not be the exception at all. They might be the key. Here is what I mean. Every time physicists have tried to reconcile general relativity with quantum mechanics, the two theories that together describe essentially everything we can observe, the mathematics breaks. The infinities pile up. The logic collapses. But when researchers began using black holes as a kind of laboratory, as a thought experiment pushed to its absolute limit, something extraordinary happened. The contradictions didn't disappear. They became informative. Think about what a black hole actually demands from us. It forces gravity and quantum mechanics into the same room and locks the door. There is no escape, no approximation that lets you ignore one to simplify the other. That pressure, that unavoidable collision, has produced some of the strangest and most profound ideas in the history of physics. One of them is this: space itself may not be fundamental. It may be something that emerges from something deeper, a structure woven from quantum information, from entanglement, from relationships between particles rather than from coordinates in a void. The holographic principle, born directly from thinking about black hole entropy, suggests that a three-dimensional volume of space can be fully described by information encoded on a two-dimensional surface, like a photograph that somehow contains the full depth of the scene it depicts. Not a metaphor, an actual mathematical correspondence. What that means, taken seriously, is staggering. The three dimensions you move through every day might not be the bedrock of existence. They might be a projection, a derived property, something that looks fundamental from the inside because we are entirely made of it, the way a character in a film has no reason to suspect there is a screen. And then there is the question of time. Inside a black hole, time and space effectively swap roles. What was once a direction in space becomes a direction in time, and it only flows one way. You cannot stop falling toward the singularity any more than you can stop moving into the future. Black holes do not just warp time. They reveal something about what time actually is. Not a backdrop, not a stage, but something deeply geometric, something entangled with the structure of the universe in ways we are still only beginning to map. None of this is settled. Physicists will tell you that openly. The holographic principle is not a proven theory of quantum gravity. It is a correspondence, a clue, a torch held up in a very dark room. But the room is less dark than it was 30 years ago, and the shape of what's in it is starting to become visible. What black holes have done, their true gift, if you want to call it that, is force us to take seriously the possibility that our most basic assumptions about reality are not wrong, exactly, but incomplete. That space, time, information, and gravity are aspects of something unified and strange that we do not yet have the full language to describe. Physics has been here before. Every time it hit a wall, the wall turned out to be a door. Newtonian certainty gave way to relativity. Classical determinism gave way to quantum probability. Each transition felt like the ground shifting, like something solid turning out to be standing on nothing. Black holes may be forcing the next transition. And here is what makes that thought not just intellectually interesting, but genuinely urgent. We may not be as far from the edge of that transformation as we think. There's a number that doesn't get talked about enough. It's the distance from Earth to the nearest known stellar mass black hole. And depending on which one you're counting, it's somewhere between 1,000 and 1,500 light years away. That sounds enormous, and in everyday terms it is. But the Milky Way is 100,000 light years across. Do that math quietly for a second. We're not in the middle. We're not safely removed. We are living inside a galaxy that is absolutely riddled with these things, with estimates suggesting there could be anywhere from 10 million to 1 billion black holes in our galaxy alone. And we have only found a handful. The ones we haven't found are not waiting politely. Here's what makes this more than just a cosmic geography lesson. Black holes don't just sit there. They shape the fabric of space-time around them. They bend light. They warp time itself. The supermassive black hole at the center of our galaxy, Sagittarius A, has a mass 4 million times that of the Sun, and it is actively influencing the orbits of stars we can observe, stars that have been clocked moving at over 25 million kilometers per hour, just from being caught in its gravitational grip. We can see its effects. We are inside those effects. The question isn't whether black holes interact with us. The question is how much we've been choosing not to look. And this is where something shifts. Because the closer you look at black holes, the more you realize they're not anomalies in the universe. They're not mistakes in the code. They might be the most honest expression of what the universe actually is. A place where the rules we trust, the rules that hold our coffee cups to tables and keep our clocks ticking in sync, are not fundamental. They're local. They're temporary. They apply to us in our corner, under our conditions. Step too close to a black hole, and every law you've ever counted on starts to negotiate. That's not a poetic metaphor. That's the physics. Time dilation near a black hole isn't theoretical anymore. We've had to correct for versions of it in GPS satellites, which run on clocks that tick differently at altitude than they do at sea level. If that effect is real and measurable in the weak gravity of low Earth orbit, imagine what it means at the event horizon. Imagine standing, conceptually, at the threshold, watching the universe outside age and fast forward while you feel nothing unusual. The universe aging around you, stars dying, civilizations rising, and you still in the first second of your fall. That image should do something to you. And if it doesn't, sit with it a little longer. Because what black holes have been teaching us, quietly, through every paradox they generate, every equation they break, every physicist they drive to beautiful frustration, is that reality is deeper than we assumed. Not in a mystical sense, in a rigorous, mathematical, experimentally pressured sense. The information paradox forces us to reconsider whether information can truly be destroyed or whether it must be conserved in ways we can't yet see. Hawking radiation suggests that even the most absolute boundary in nature, the event horizon itself, is not perfectly silent. That quantum mechanics bleeds through. The holographic principle asks whether the three dimensions we move through are somehow encoded on a two-dimensional surface, like a projection we've mistaken for the original. These aren't fringe ideas. They are the live edge of the hardest thinking our species has ever done. And we are doing it now. Right now, with the telescopes we've built, the images we've captured, the equations being argued over in rooms full of people who have devoted their entire lives to this. The photograph of M87's black hole wasn't just a photograph. It was a proof of concept, that we can look into the darkest place in the universe and see something real, that we don't have to take it on faith, that the physics holds, and where it breaks, we will find the deeper physics waiting underneath. We started this journey asking what a black hole is, and the answer, after everything, is that a black hole is where the universe stops pretending. It's where gravity wins so completely that light itself cannot argue with it. It's where our best models of time and space get stress-tested to destruction. It's a laboratory we can never enter, and a mirror we can never look away from. And maybe that's the most honest thing physics has ever given us, not certainty, but the precise location of our uncertainty. Not an edge that terrifies, but an edge that calls. Because every time science has reached a boundary it couldn't cross, something cracked open, something new came through, the photoelectric effect, quantum mechanics, relativity itself. Each one started with an anomaly that wouldn't go away. Each one ended with a revolution. Black holes are the anomaly that won't go away, and we are closer to understanding them, and closer to them physically, cosmically, than most people ever stop to realize. That proximity isn't a threat, it's an invitation to keep looking, to keep asking, to stay honest about how much we don't yet know, and to feel the strange privilege of living in a moment when the questions are this good. If this made something click for you or opened a question you didn't have before, subscribe so you don't miss where we go next, because we are nowhere near finished. Like the video if it earned it, and leave a comment with the idea that hit you hardest. Genuinely curious what lands. See you in the next one.